solving between 0 and 2 pi, get tan by itself, you get negative root 3, 1 over root 3. That is on your unit circle. You might have to rationalize the denominator. If you wrote yours on the unit circle as negative root 3 over 3, you need to be able to recognize that 1 over root 3 is the same. That's your pi over 6 family. Tan is negative in quadrants 2 and quadrants 4. So you put your answer in quadrant 2 and quadrant 4. And this would be the answers for this, between 0 and 2 pi. I could, chapter 6 could do this. Chapter 6 could change 0 to 2 pi to 0 to 4 pi. You see that you would get 2 more answers because you'd have to have one here coterminal, one here coterminal. How do we find coterminal angles? We can find a coterminal angle by adding 2 pi one more time around the circle. And you're going to get really good at changing 2 pi things to over different denominators. Does it make sense that 2 pi is 12 pi over 6? So coterminal with 5 pi over 6 would be 17 pi over 6. And coterminal with 11 pi over 6 would be 23 pi over 6. So a chapter 6 question could give you a different domain. What we do in chapter 7 is, instead of having a restricted domain, we just say, you need to write everything. Like 0 to 4 pi is twice around. If I did 0 to 6 pi, that'd be 3 times around. If I did 0 to negative 2 pi, that'd be once around in the negative direction. But if I say theta belongs to the real numbers, that means every single possible answer. Does it make sense? There's going to be an infinite number of them. So really, the new idea in chapter 7 combines 2 ideas in chapter 6 together. So it's nothing new, it's just putting 2 ideas from chapter 6 together. The one idea from chapter 6, and I'm going to change this back, okay, is you've solved between 0 and 2 pi. So I'm going to erase these 2. Right? There we go. You've solved between 0 and 2 pi lots. That's in chapter 6. And when we do theta ER, that just means combine the idea of, remember when you wrote all the coterminal angles with something? You added 2 pi times k and added 2 pi times k as many times as you wanted where k was an integer. So we do the coterminal idea again. And for whatever reason, instead of doing 2 pi times k, they put the k in the middle. It means exactly the same thing. But now we say 2k pi instead of 2 pi k. But it's adding or subtracting 2 pi as many times as you want. Because here are my 2 answers, right? If I go this one and go all the way around, I'd get it again. If I go all the way around, I'd be coterminal again and again and again. So chapter 7.1, our first idea, the general solution, is just combining 2 ideas from chapter 6. Do you remember how to solve between 0 and 2 pi? Do you remember how to write all the coterminal angles with something? That one you might have forgotten. So it's good to review. And we combine them together and we write our answer like this. Now, if you got this question, I want to point out something. If you got this as a multiple choice question, and this didn't show up as an answer, this only happens with tan. Tan happens to always be right across from each other. So another way to write the answer would be to say, start with one of them, 5 pi over 6, and instead of going all the way around, does it make sense that I would get to the other one by going halfway around, which is pi? And then going halfway around gets me back to, so if I go 5 pi over 6 plus k pi, then I'd just be jumping halfway around, and I would still get every single coterminal answer that exists. This is just in case it comes up on a multiple choice question. Because that might appear, and you'd be like, oh, I got this as my answer. To recognize with tangent, you can do plus k pi. kind of makes sense. What's the period of tangent when we drew the tangent graph? The period was pi. So it's going to repeat itself every pi on the graph, which means we can get our answers every pi if we wanted to write every coterminal one as a result. So at the top of page, I'm going to open it up here. You have some space. 7.1. You did these, hopefully you did these examples on page 573, but you have some space at the top of page 574, and I want you to write the steps for the general solution. And in the questions, sometimes they'll say, find the general solution of blah, 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 or sometimes they'll give you the domain, theta ER, or sometimes they'll solve and say nothing. And technically that means you have to do the general solution. Usually they're nice and say something. But sometimes if it just said solve sine theta equals 1, you have to solve for everything. So it's a general solution. And then you can put an X through the actual question number 1. We're not going to do that question. We're going to do our own question number 1. So you can put an X through it. And right below this, is everybody done? Good. Right below this is going to be our example 1. Solve for theta, where theta belongs to the real numbers. And we're going to start with 7 sine theta plus 1 equals 0. This will be a calculator question. So according to the steps that you wrote right above this, you start by solving between 0 and 2 pi like you normally would.
Would you have to use radians or degrees for this?
You would, if it doesn't say, they'll assume radians. So if it has a theta ER, we're going to assume radians. Okay. When you get to calculus, technically calculus works with degrees, but it's really complicated. Calculus works really nicely with radians. So we start to go, now we're getting into higher level math, all that baby level math with degrees up till grade 11 pre-calculus. Baby level math. Okay, grade 11 pre-calculus is still pretty tough. But now we're switching mainly to radians. So sine theta equals negative 1/7. And you'll do sine inverse of positive 1/7 to get your reference angle. How many of you have your fractions to decimals memorized? Like some of you have something like, you know what 1/2 is a decimal? Right? What about 1/3? Yes, 1/4. So you've got some of them. 1/5. Is 1/6 the first one you don't know? 1/6, 0.16 repeated? Does anybody know 1/7? It's my favorite fraction. Okay, I'm sorry, I have to get off topic a little bit, and then I get back on topic and off topic, because there's some fascinating things that, because you don't know that 1/7 is 0.142857 repeated, because you don't know that, You didn't recognize that the reference angle is almost identical to 1/7. You just missed that, okay? But here, just off topic a little bit, why 1/7 is my favorite fraction to a decimal. It's actually easy to remember. Because if you double 7, you get 14. If you double 14, you get 28. If you double 28 and just make a little mistake, you get 57. And that repeats itself forever. 1427857, 1427857 forever. Which is pretty cool, because it's pretty easy to remember, it's that doubling thing. And it's a pretty crazy fraction for repeating itself. 6 things repeating themselves, that's a little crazy. But then the crazy thing happens is that if you know 1/7, you can do all of the other 7s. Like 2 7s. What's the next biggest number in here after the 1? It's the 2. 2 7s happens to be 0.285714 repeated. What's the next number after 2? The 4, right? 3 7s happens to be 0.428571 repeated. I think that's super cool for the 7s. Okay, that's why 1/7 is my favorite fraction. Now, here is an interesting thing about 1/7. Well, it appears to be interesting with 1/7. In radians, if I would do 1 divided by 7, just so you know that I'm not lying, look at that. 1428571, 142, oh, it rounded up to the 9. But it repeats itself. Now, interestingly, is if I did sine inverse of 1/7, notice how close they are. This is the crazy thing about radians. Is if you put in any fraction close to 0, one divided by 11, 0.0909. Sine inverse of 1 divided by 11. Oops, that's close to an 11. Oh my goodness, that's really, really close. All the way through that happens. So when I figured out this number, I was like, well, that's interesting. But if you didn't know 1/7, you'd be like, whatever. And what's kind of frustrating with this question is the student that does it wrong and just typed in 1/7 and got 0.143, you can't tell if they didn't know what they were doing. And then we solve between 0 and 2 pi. So sine is negative in quadrants 3 and 4. You get 3.28 and 6.14. And then for the general solution, you just add 2k pi. So let's call this one 1A. I'd like you to try. Everybody got these numbers down? If you don't, just make up some numbers. It's not like you'll ever check them, right? You'll just assume you know what you're doing. This one I want you to try. We'll call this one B. I will just put up the answer, so you do need your calculator. You do need to try. You want to see if you can get the answer. All right. Did you get those as your answers? So your work, what would you have to have done? You would have had to get cos by itself, which would have given you cos theta equals -1/5. Then you'd have to find your reference angle by doing cos inverse of +1/5, right? Because we always find a reference angle with positive values. Which probably means on the exam and on tests and quizzes, about 90 to 95% of the time, teachers put -1s to check that. Does it make sense? Because if you do the +1 and you forget to change it to the positive, you're fine. But if you do the -1 and you forget to change it to positive, you get a mistake. Almost always you have -1s, because then they can check that. See if you remember that. Then once you have that reference angle, you do pi minus your reference angle for quadrant 2 and pi plus your reference angle for quadrant 3. And then because it's a general solution, you go plus 2k pi. All right, and then part C, we are going to up it a level. Are you ready to up your practice for chapter 6? What's something from chapter 6 you probably need to practice? Your quadratic formula with trigonometry. Oh, look at all those happy faces. Some of you are like, I've never heard of this quadratic. Okay, on your formula sheet, it has the following. So you don't have to have it memorized until next year for those of you in AP Calculus. In AP Calculus, there's no formula sheet. So all the formulas from grade 9, 10, 11, and 12, you have to know. So one of the things I recommend is like something like the quadratic formula. Start working on memorizing every formula this year already, so you have it available for next year. Now, on your formula sheet, it has for x squared, we have tan theta. Okay? This one doesn't factor. So you would have to use the quadratic formula. In using the quadratic formula, instead of x squared, you have tan squared. So we'd write tan theta equals negative, the b value is 3, plus or minus. B squared will be 9, minus 4, the a value is 1. The c value is -7 all over 2 times a, which will just be 2. And because of that plus or minus, I'm going to split it up because it's going to give us 2 separate ones. One of them will be -3 plus, and I'm just going to simplify that, 28 plus 9, 37 over 2. And one of them will be with the minus, so tan of theta will equal -3 minus square root of 37 over 2. Now split this up and do each of these separately. I sometimes find with these fraction ones with the quadratic formula that it is not intuitive and right away, like, do you see this one's positive and this one's negative? Maybe. But you have to do a little bit of mental math to make sure this one's positive, and a little bit of mental math to make sure that one's negative. So sometimes I go to my calculator and I type it in to begin with. So I'm going to pull up my calculator. I like using the fraction button on my graphing calculator. -3 plus the square root of 37 divided by 2. I recognize that one's positive. And I retype it and just change the positive sign to a negative. 1.541. Put the 3 dots there. just to show I'm not rounding early. Rounding early, if it causes your final answer to be incorrect to 3 decimal places, you get an E6 error for a rounding error. But I like changing these to decimals because now I see the first one's positive. So according to my CAST rule, I'll be looking in quadrant 1 and quadrant 3. My second one is negative. According to my CAST rule, I'll look in quadrant 2 and quadrant 4. Both of these obviously are not on your unit circle. This is a calculator question. We're going to have to find our reference angle. Okay. Also, it says solve for theta and it doesn't say 0 to 2 pi. It doesn't say anything. If it doesn't say anything, it implies the general solution. You have to find all the solutions. So for my first one, I'm going to go back to my calculator. I'm going to do tan inverse. Tan inverse of this answer. So I'm going to go up and highlight it, push enter. Reference angle of 0.995. So since this was a positive one, our one answer will be in quadrant 1, and our other answer will be in quadrant 3. So I'll have to do... Are you getting good at figuring out quadrant 3, pi plus reference angle? Does that make sense for quadrant 3? Just to review, I'll write it down, 4.137. This one in quadrant 3, here's a little picture. If I wanted to find something in quadrant 3, and here's my terminal arm, and here's my reference angle, I would have to go halfway around, which is pi, and then I would have to add my reference angle. So if you think about the picture, it's going to be really easy for you to remember those formulas, right? I actually say it. Some people go, oh, I've memorized quadrant 2 is pi minus reference angle, quadrant 3 pi plus reference angle, quadrant 4 2 pi minus reference angle. Don't memorize them. Just imagine the picture in your head and it's obvious that it's pi plus the reference angle. Your brain is going to have so much that it has to remember. If you memorize things without meaning, it takes up way more brain space than you need, and your chances of forgetting it are way bigger. If you have something that makes sense to you, remembering it is way easier. And so our goal is trying to remember, like we have to remember a lot of stuff in this course. There's a lot of details. So our job is to try and remember as much of it in the easy way as possible, that it makes sense. Some of it, you're just going to have to memorize because it's like, that doesn't make sense. And that's okay. Sometimes when we learn things, we're actually incapable of fully understanding them when we need to know them. And we have to rely on, I just know what I have to do. I have no idea what is actually going on. Have you been there? Yes. It's like, I live there. Yes. But the interesting thing is, as time goes by, like if we would look at some of the things that you did for that in grade 9 and look at it now you'd be like, oh, I totally get that now. But you didn't get it in grade 9. Some of this too. You won't get right now. But if you keep studying, all of a sudden university, you look back and be like, oh man, I wish I could go back to grade 12 pre-calculus. That was so easy. And you'd be like, and your current self would be like, I want to punch you, right? Okay. So there is the first one. We're going to do the same thing for the negative. A little bit tricky here because when we do tan inverse of that, we have to do tan inverse of positive. So I go to my calculator. I'm going to go tan inverse. I want to steal this number with all of its decimal places, but I want it to be positive. And when I push enter to steal that number, it keeps the negative. So I can either cursor all the way over and get rid of that, but I'm lazy. So I'm just going to multiply it by -1 to make it positive, because that's quicker. Only 3 buttons instead of 8 buttons to go all the way across. Push enter and my reference angle is 1.354. And because tan is negative, I'm going to look in quadrant 2 and quadrant 4. Again, pull up my calculator. Quadrant 2 is going to be pi minus my reference angle. Quadrant 4 is going to be all the way around 2 pi minus my reference angle. And sometimes I use the store button on my calculator. Right above the on button is store. I store it as x because I know I'm going to have to use this number a couple of times. And now it just becomes, oh, if I want to do pi minus my reference angle, I can just go pi minus x. It's really quick. And when quadrant 4, when I want to go 2 pi minus my reference angle, I can just go x because I've saved it as x. It doesn't affect anything later for graphing. It will remember what you saved as x until the next time you save something as x. So it doesn't affect any other your calculations if you store it as x. We get 1.788 and 4.929. I'm going to just make a little note here. This is going to happen a lot, this note. The majority of the time, you're going to be asked to solve between 0 and 2 pi. Up to this point, this is a chapter 6 question. You could have this on your chapter 6 test, but in chapter 6, I'd probably say, what are the answers between 0 and 2 pi? The only new thing in chapter 7 is now that it's a general solution, we just write all 4 of these and all their coterminal angles. So I'm going to write...
Hello, can I please have Laura to the office?
Yeah, she'll be right down.
Thank you.
So I'm going to write all of them, 0.995. It doesn't matter. Some people like to write them from smallest to biggest. It doesn't matter. I just wrote them in the same order that I had them. And I add 2k pi to each of them to do all the coterminal angles. And I have to define k as an integer. So now I've done the general solution. So the first new idea today, the general solution, is just combining 2 ideas you already knew. But there will be no general solution question on your chapter 6 test. It will be on your chapter 7 test. But you will have coterminal angles on chapter 6, and you'll have solving 0 to 2 pi on chapter 6. So this is a good review for chapter 6. Okay, you can circle questions 5, 6, and 9.